For the last lesson in this unit, we're going to be discussing parent functions and transformations. Now, you've probably been introduced to the idea of a transformation in geometry when you took a two-dimensional object or shape on a coordinate plane and then you either did a translation or reflection or rotation. So that's probably a concept that you should be familiar with. We're going to extend on this, and we're going to focus on a handful of different types of transformations. We're going to work on translation and reflection, which you should be familiar to you, and we're also going to work on something called a compression or a stretch. And you may have heard the term dilation or scale factor in geometry, and that's how that relates to compression and stretch. And so what you're going to find in algebra is that we have a number of different what we call families of functions, and each family of functions has a single basic function that all movement of transformations work off of. And you can see here our parent linear function is y equals to x. So let's take a look at our first one. We're going to start with translation. And so a translation, as you can see, is just a shifting or sliding of every point on the figure. So we are just going to be shifting or sliding left to right, or up and down, or a combination of both. We may be able to shift a function to the left and then up, or to the right and then down, or vice versa. And so it's very important that you understand how a translation works. And so you can see here in the first one, a vertical translation is when we add a value to the entire function, the entire base function or parent function. Now, we're going to be using K to represent vertical translations for the rest of the year. And if you look at the second part of this, H is a translation that actually moves it horizontally. It's going to move it left or right. So H and K are going to be a part of your terminology of translations all year long, no matter what we're working with. Now, one thing that you need to be aware of, whenever we add or subtract a unit, a vertical translation, it does exactly what is suggested. So if it says plus 3, we're actually going to move up 3. If it says minus 2, we're actually going to move down 2. However, with the H, it actually does the opposite of what we have given. So if it says plus 2, it's actually going to go to the left 2, and if it says minus 1, it's going to go to the right 1. So a couple things that you're going to need to pick up on as we go through this. So let's take a look at our first sample problem. Go ahead and read sample problem 1, and then plot the original point, and then do the translation and answer the following questions. Okay, so if I start with -2 and a +5, I start right here, and it says to translate it 3 units left. So I'm going to come over 3 units left, and then 2 units down to get my resulting new point. And so my resulting point is now -5, +3. When you translate the point left to right, how does it change the coordinate on the point? Well, when we do left to right, it actually changes the x values. And then when we translate the point up or down, this actually changes the y values. For our next transformation, we're going to talk about reflection. And you can see as reflection is a transformation that reflects or flips a graph across a line, which we call a line of reflection. Now, initially we're going to start here by reflecting our graphs or our functions across either the y-axis or the x-axis, but keep in mind that you can also reflect any figure over any given line or point over another point, so it won't just be the x and the y-axis. However, that's how we will start today. So I'll give you a quick visual here with the black graph being f of x, and you can see when we reflect it across the y-axis that all of the x values actually change place, and so that's kind of given to us in this little part right here. We see that when we reflect over the y-axis that the x is negated. Now, on the other side of that, if we reflect over the x-axis, the y value is negated. And you notice here we say y, or we say negative f of x, but if you recall, y is the same thing of f of x. So if we negate the y, which is what's happening in that reflection, we're also negating the f of x. So that's in effect doing the same thing. So if we reflect over the x-axis, we're negating the y, or the entire f of x function. So since reflection is something that you should have covered in geometry, I hope that this is somewhat familiar to you. We have a sample problem for you to work. So if we'll move on down to sample problem number 2, go ahead and pause the video and try to work that on your own to start, and then come back in a second and take a look at the solution. Okay, so if I want to reflect this basic graph across the x-axis, I need to find the points that correspond to the given points in the original function. You can see I've listed them out in this table already. So basically, we've got 1, -2, we've got 2, 2, we've got 4, 2, and we've got 6, 4. So I want to reflect those basic points across the x-axis. Now, the way I'm going to do that, I'm going to simply take this point, and I notice that it's 2 units down from the x-axis, so I need to go to the other side and go 2 units up. And I basically need to do the same thing with the other points on the graph. So same, I'm going to go opposite of that. And then of course this is 1, 2, 3, 4 up, so I got to go 1, 2, 3, 4 down. And so now that reflected graph creates a mirror image of the original graph. Now, what I need to do is I need to put that information in this function, in this table representing the transformation. So the first one is 1, 2. The next one is 2, -2. We have 4, -2, and 6, -4. So the next question asks, how do the y coordinates of the points change after being reflected over the x-axis? And you can see here that these points in relation to those points are actually opposite values. So it's either, you could say it's either negating the values or it's making them opposite values. The next question says, how do the x-coordinates of the points change after being reflected? And you can see by looking at those values right there, there is actually no change. And so we could just simply say no change. Okay, so if you didn't have any trouble working that problem, you've got a pretty good basic understanding of reflection and starting this as we move into other parent functions. The final transformations that we're going to work on in this particular lesson are what we call compression and stretch transformations. Now, in geometry, you may have heard of a term called a dilation or something called a scale factor when you did similar poly. Compression and stretching a function in algebra is very similar to a scale factor or dilating the function. Basically, what's going to happen is the value that we're going to take is going to be multiplied to the function. It's going to create this kind of this lengthening or shortening the given function. And so we can have vertical compression and stretch. We can also have horizontal vertical and stretch. For right now, we're just going to focus on the vertical compression and stretch. And you can see that through the definition here and through the given graphic example that when we multiply a value larger than 1, you kind of get this lengthening or this stretching of the function. And so you can see the red graph is representing that, with the blue graph being the original function. Now if we were to multiply it by some fraction between 0 and 1, it would actually compress it a little closer to the x-axis there and kind of shrink it in a little bit, and that's represented by the actual green graph. And so you can see what a multiple simply does to a given function. So, and you can see in the equation y equals a times f of x that the a value is being multiplied times the function, and it acts as that scale factor. So just keep that in mind, a scale factor or a multiple. That is pretty much all compression and stretch is. We will work more specifically on the different types of vertical stretches and vertical compressions versus horizontal stretch and compression as we get into each individual parent function. It may take a little bit of individual work for you to have a clear understanding of what it does to each individual function. However, here in sample problem number 3, we just have a basic function. And so what I would like you to do, just in case you don't understand what this problem's asking, remember f of x is just simply representative of y. Okay, and so we're going to graph these points x and y, or x and f of x. Then we're going to see how g of x relates. And so basically g of x has a multiple of 3 times f of x. So this is going to vertically stretch our original graph. So what I want you to do is to go ahead and fill in the remainder of the table. Use the x value for both f of x and g of x and see how it stretches. So go ahead and take a second to see if you can get a clear picture of the stretch. If you do this correctly, you'll pretty much know you did it correctly when you finish. So go ahead and pause the video and work that, and then come back and see the solution. Okay, so I'm going to start by actually just focusing in on this part of the table. So now I'm going to take my final f of x value and I'm going to multiply that value by 3. So I'm actually multiplying the output, or the whole function, by 3. So I'm going to say 3 times 2 is 6, 3 times negative 3 is negative 9, 3 times 1 is 3, and 3 times negative 2 is negative 6. Now I'm going to match up these x values with g of x, which is kind of our output values with our new multiple. So g of x is also now, if you think about it this way, y is equaling to f of x in this first function, but in our second function, y is equaling to g of x. And we're using g of x and f of x to basically define two separate functions, but the x values are going to be the same accordingly. That's what the x in g of x and the x in f of x is telling us, that we're using those same x values here. So let's take a look. So I'm going to say negative 5, 6. So negative 5, I'm going to go up 6. And then I'm going to go negative 2 and a positive 6. Now I'm going to go 0 and negative 9, which is, well, it's way down here. It's below where a graph gives us. Then I'm going to do 3, 3, and then lastly 5, negative 6. So that's kind of down here. And then I'm going to connect those dots. And what you can see there is we have a very, very similar looking graph that looks like if you just grabbed it on both ends and pulled it away from the x-axis, you're stretching it out away from the x-axis. And so that is a vertical stretch. And we've multiplied all of the original values in the first function by 3, thus giving us a scaling of 3 on there. So that's a good introduction to compression and stretch. This will be something that we're going to work with all year, and if it's not clear the first time you see it, that's okay. The more you work with it, the better and better it gets. So if you have any questions, be sure to ask questions in class.